In this video, we're going to be talking about some applications of differential equations. So there are many real-world applications of differential equations. Examples include population growth, radioactive decay, thermodynamics, investment growth, chemical reactions, and more. These applications often describe rates that are proportional and can be represented by the differential equation dy dx equals ky. We've also learned in the past about exponential growth and decay. So exponential functions model growth and decay, and the equation y equals ce to the kt power can be used to represent growth and decay. C represents the initial value, k represents the constant of proportionality. So we can use that equation when we have exponential growth or decay, but one indicator this can be used is a phrase such as, the rate of growth is proportional to the amount present. So for some practice questions here, number 1 says, find the general solution to the differential equation dy dt equals ky to show the connection to the model for exponential growth and decay above. So let's say I have this differential equation. So dy dt equals ky. If I separate my variables, so I'm going to multiply both sides by dt. Then I'm going to divide by y. And now I'm going to integrate. So I'm going to get ln of absolute value of y equals kt plus c. And if I find my general solution by putting e on both sides as the base, I'm basically going to be getting y on the left equals e to the kt plus c on the right. Now, using logarithm and exponential rules, this is equivalent to e to the kt times e to the c. E to the c is just some constant, and we can rewrite this as y equals ce to the kt. So now we have shown that that differential equation dy dt equals ky is equal to y equals ce to the kt power. All right, let's take a look at some real-life examples now using all of that information. So a cup of coffee is 200 degrees after being freshly brewed, so that's at t equals 0. The rate of change of the temperature of the coffee, y of t, at time t in minutes can be modeled by the given differential equation. And we're asked to find the temperature of the coffee after 5 minutes. Okay, so the first thing that I'm going to do is I'm just going to rewrite this differential equation here. So dy dt equals negative 0.04 y minus 70. I'm going to multiply both sides by dt. And I know that I'm trying to separate the variables here, so I'm going to also divide by y minus 70 on both sides. You could also think about that as multiplying by the reciprocal, so multiplying by 1 over y minus 70. And now I have successfully separated the variables. That is always step 1 on a differential equation problem. Get one variable all on the left, the other variable on the right. Once you do that, you can basically integrate both sides and find the antiderivatives. So over here, I'm going to have ln of absolute value of y minus 70 equals negative 0.04t plus c. Now I'm going to try and get y by itself. And using some log rules, I'm going to get y minus 70 equals c e raised to the negative 0.04t power. To get y by itself, y equals ce to the negative 0.04t plus 70. So this is what we have as our general solution. Now in this problem, we are given an initial condition that allows us to find the particular solution. So we know we have this point 0, 200. So what I'm going to do is I'm going to plug that in for t and for y. When I do that, e to the 0 power is basically part of this problem, which is 1. So I really have 200 equals c plus 70, and then we could determine here that c is 130. So our particular solution is y equals 130 e to the negative 0.04t plus 70. Now this problem is asking us to find the temperature of the coffee after 5 minutes. So that's what we would get when we plug 5 in. And since I don't have any rounding rules here, and often if this is on the AP exam, we are not in a calculator section. So I'm going to leave my answer just like that. Okay, let's take a look at another one. This one has to do with half-life, which is something you might have learned before. A radioactive substance has a half-life of 5 years. It decays exponentially, where the rate of decay, d of t, is proportional to the amount of time at time t. If there is initially 100 grams of the substance, how much will remain after 10 years? So notice the difference between this question and the previous one. There is no equation given to us here. But I have a few clues that can help us get an equation. So I know I'm talking about exponential decay. I see this phrase is proportional to the amount at time t. So I know that that equation that we wrote on the previous page earlier in this video, I know that I can use that equation on this problem. So that's y equals c e to the kt power. Now, c represents here the initial amount of the substance. K, I do not know what it is, and I know the half-life is 5 years. So half-life is basically saying that after 5 years, half of the substance is remaining. So I know then that basically I'm going to be at 50 grams of the substance after the 5 years. If I divide by 100 on both sides, I'm going to get 1/2 equals e to the 5k. The 1/2 will always be the case on one side when you are doing a half-life problem. So now I want to figure out what k is, the constant of proportionality. So I'm going to take the ln of both sides. That's going to give me the ln of 1/2 equals 5k, and divide by 5. K is equal to the ln of 1/2 over 5. Okay, again, I'm going to assume that this is a no calculator question, so I'm just going to leave my value of k like that. Now we're asked how much of the substance will remain after 10 years. So we know we initially were at 100. We know that k is ln of 1/2 over 5, and we want to figure out how much there will be after 10 years. Now, we could leave our answer like that, but we could also determine, if we did have a calculator, you could put it in and see that that's going to give you 25 grams. Or we can just make sense of this problem, right? If the half-life is 5 years, that means every 5 years, the amount of the substance is being divided by 2. So if initially at t equals 0, you had 100 grams. After 5 years, we said there would be 50 grams, which is half of 100. So after another 5 years, it's going to halve again, and therefore that gives us 25 grams. Okay. Not all questions will come out to clean numbers like this, so it's still important to walk through the process like in this question. All right, let's try one more here. The number of bacteria in a petri dish is growing at a rate of 1,000 e to the 0.5 t, where t is time in hours. At t equals 0, there were 500 bacteria in the petri dish. Find the number of bacteria present at t equals 6. So I have an expression in this problem, not a full equation, right? If I look back at number 1, the left side of the equation was given to me. In number 2, we were given no equation at all. And here it's like I'm just given half of it, right? I know one piece of it. So I have to determine what's going to be on the other side. I know that this is a differential equation because I see these words growing at a rate. So I'm going to say that this is dy dt equals 1,000 e to the 0.5 t. Really there we should be guessing between y and dy dt. Since we're talking about a rate, that's why we're picking the differential one and we're picking the derivative. I'm going to now solve this differential equation by moving dt to the other side. And that's enough to separate the variables, and we can now integrate. Over here, I'm left with just y, which is great. Remember, we're integrating essentially 1. Over here, when I think about this is going to be an application of chain rule, or reverse chain rule for that matter. So the derivative of the inside there is 1/2. So it's like we have a 1/2 here, which is essentially going to put a 2 out here. Okay. There are different ways you can think about that. So if you write yours differently than I have here, it should come together in just a second. So this is essentially going to come out to be 2,000 e to the 0.5 t plus c. Now let's plug in our point that we know. So we know at t equals 0, there were 500 bacteria. E to the 0.5 times 0 is just going to give us 1, right? That's e to the 0 power, which is 1. So I have 500 equals 2,000 plus c, and c is negative 1,500 then. So let's put that all together. I'm going to zoom out here to get our particular solution, which is y equals 2,000 e to the 0.5 t minus 1,500. And then we're asked to find the number of bacteria at t equals 6. So I am just going to plug in 6 for t, and I'm going to leave my answer just like that.